All right, open up your book to section 1-3. We are on page 15 in your book. And the title of this section is Dilation and Translation of Function Graphs. And basically what we're going to do is look at transformations of graphs. Transformations is the category that dilations and translations fall under there. So our objective here is transform a given pre-image function so that the result is a graph of the image function that has either been dilated by the given factors or translated by the given amounts. Again, dilations and translations fall into the category of being a transformation. All right, so let's start out with a few terms here. Let's define what a dilation and a translation are. These are hopefully terms that sound familiar to you from geometry. But a dilation is a transformation that stretches or shrinks an object. Now in geometry, you're stretching and shrinking a triangle or a circle or whatever it might be. Here we're going to be talking about transformations of functions, but it relates to any type of object. So a dilation is a stretch or a shrink of an object. A translation is a transformation that moves or shifts an object. So the dilation is going to make something bigger or smaller, versus the translation is going to keep the same size but move its location. We're moving it left or right, up or down, or shifting it, however you want to describe that. Dilation and translation, those are the two that we're going to study here in this section. As you saw in the objective there, we used a couple of new terms there perhaps for us, the pre-image and the image. Hopefully the word or the prefix pre in front of that helps us know which one's which here, but the pre-image is your original untransformed object. So that's what you're starting with. In our case, it's going to be a function that you're starting with. And then when you do some sort of transformation to that function, you end up with an image. That's the transformed object. So the pre-image is the original, the image is the result after the transformation. All right, we're going to start with translations first. It's kind of the opposite order that the book is doing them in, but we're going to do translations first because I think that's the easier of the two to deal with. And we'll start with the vertical translation. So let's suppose that we have this graph here, these two functions here. One is a transformation of the other. And let's suppose that we want to translate function f of x up 2 units to get g of x. So if I want to translate function f of x up 2 units to get g of x, and that's what you see in this sketch here, the question is, how do we do that? How could I write what the relationship is between these two functions? Well, to do that, let's create a table of values for us to work with here. We're going to write down what is happening on function f of x and what's happening on with the corresponding points on function g of x, and use that to help us understand how to go from f of x to g of x. So let's pick the 3 key points here. We're going to use this same graph here on the next several examples. So I'm going to be using the same 3 points here. I'll just mark those on this first sketch, but I won't mark them every time here for the ones that follow. But we'll use those 3 points because I can easily see where those 3 points have been moved to. And we'll write down what the original 3 points are and where they've been transformed to. So the first point there is at -1, 0. The second point is at 0, 1. And the third point there is at 1, 0. So those are the 3 points that we've picked there to start off with. And the question is, where did they move to? Where were they transformed to on function g of x? Well, I can see that they've moved up there. So the point that was at -1, 0 is now at -1, 2. And the point that was at 0, 1 is now at 0, 3. And finally, the point that was at 1, 0 is now at the point 1, 2. Now, What I want to do is look at this data and use it to help me figure out what exactly happened and what the transformation is that took place and how I can write the relationship now between f of x and g of x. The first thing you should note here is that the x values didn't change. If you look at the x values in function f of x that we wrote down, those are the exact same x values. The first point in the ordered pair there are exactly the same. So it's the second values that I'm looking at, the y values. And that's what I want to compare. If I take this first set of numbers right here, or sorry, the second set of numbers right here, and compare them with this set of numbers right here, the question is, how are those related? And so I went from 0 to 2, and then 1 to 3, and then 0 to 2. It looks like there's a difference of 2 here. And in fact, I'm going to think of it this way here. If I were to go from g of x to f of x here, that I can see that really what I've done is I take each of the y values that I see on function g of x. If I subtract 2, I end up with the values that I see on function f of x. And so I can write this then, that function g of x, if I take function g of x and I subtract 2 from each of those y values, remember g of x represents the y value, the dependent value. If I subtract 2, that ends up giving me f of x. That's, of course, one way that you could write it. You could also take that 2 and move it to the other side, and you could say g of x is equal to 2 plus f of x, which this is actually going to be the way that we write it. But I wanted to point out to you here in this one that I could write this as either addition or subtraction. And really, the first one here is really one that's kind of telling the truth of what's happening here, because this is associating the value of my transformation with the appropriate variable. The g of x there is the y value on function g, and I can see that I'm subtracting 2 to get back to function f of x. And I want to point that out to you because that'll play an important role here in our next translation here, or it kind of helps us see why one is written one way perhaps and one is written another way. All right, so that right there is our vertical translation. Let's take a look at a horizontal translation. Again, we're going to look at the same functions here. Well, I should say the same pre-image, f of x, but obviously the image is going to be different here because I'm translating it different. Now I'm doing a horizontal translation. But I want to translate function f of x to the right 4 units to get g of x. And again, to help us come up with the relationship now between function f of x and g of x, let's just draw a table of values. This is a real nice way to look at this and to help you make sure that you understand how you're going from one to the other and why you end up with the equation that you end up with when you do that. I'm going to pick the same 3 points on function f of x, so that would just negative 1, 0, 0, 1, and then 1, 0. Really, I only need 2, but I'm going to pick 3 just so we can look at all 3 of those and see how they've changed. Now compare those to function g of x and where those points have been transformed to. So the first one there at negative 1, 0 is now on function g of x at 3, 0. Let's move to the right, just like we said above. That's what we're trying to do, a horizontal translation to the right. The point that was at 0, 1 is now at 0, 4. The point that was at 0, 1 is now at 4, 1. And finally, the point that was at 1, 0 is now at 5, 0. All right, and again, the question that you want to ask yourself here is, well, if I look at the data that I have in under a function f of x, how does that relate to function g of x? What's changed? How do I go from one set of data to the next? Now this time, what you should notice is the second point, or the second value in our ordered pairs, has not changed. From function f of x, it was 0, 1, 0, and the same is true over there under g of x. So it's the first value, the x values that we're looking at here. If I look at these values right here, the question again is, how do I go from one set of values to the other? And so if I look at g of x, if I take those numbers 3, 4, 5, if I were to go and subtract 4 from each of those, I would end up with the negative 1, 0, and 1 that I have under function f of x. So if I wanted to write down then the relationship here between function f of x and function g of x, I would have to say it this way. I would say that g of x is equal to, so if I pick the x value, like if I look over here on function g of x, let me just put that in red here just so I can look at that first point. If I look at this value of x equals 3, I have to do something with that value of x equals 3 to end up with with a value of -1. So the question is if x here is 3 on function g, what do I have to do in order to end up at -1? Well, that's what the -4 here on my green arrow is helping me remember, that all I got to do is take my x value and subtract 4 from it to end up with f of x minus 4. And you can plug in a value of 3, and you should see that g of 3 would be the same as f of 3 minus 1. That'd be f of -1. Those, in fact, are the same. G of 4 is the same as f of 4 minus 4. That's f of 0. Those are the same. So there is our relationship. And again, when you look at this, many students will ask, well, why is it that we're subtracting here to move this thing to the right? That seems like a positive direction. I should be adding to move to the right, it seems like. And I'm not saying that that's not a logical way to think about it, but it turns out that's not the case. You're subtracting. And the question is, why do I do it one way here to move in a positive direction, but back here I did it another way? Here it looks like I'm adding in that second form there in order to move up. Well, the real story is you're actually subtracting in both cases. If you look at what's happening here, we're actually subtracting in order to move up in this case, because again, I'm associating the translation with the variable g of x that it's associated with. And the same is true over here, that I'm associating the variable with the value that that translation is representing, or they're changing there. It's changing the x value. So now I've got the value associated directly with that variable. Turns out you're subtracting go in a positive direction, or to the right or up each time. You do subtraction to go to the right or up. You'd use addition to go the other directions. All right, let's take a look at an example here then. Take a look at example number 2 there on page 18. And example number 2, they're going to tell us actually the function we've been working with here. The equation of the preimage of the function that we've been working with here is f of x is equal to the square root of 1 minus x squared. So f of x is equal to the square root of 1 minus x squared. And it says confirm on your grapher that g of x is in fact equal to 2 plus f of x minus 4 in the transformed image by doing the following. They ask us to do this 2 different ways. So the first way is by direct substitution into the equation. So when they say direct substitution into the equation, they're saying take f of x and g of x and actually replace f of x with what it's equal to. So we'll do that, and then we'll graph this. So they're saying that g of x is equal to 2 plus f of x minus 4. And so when they say by direct substitution, they're saying take function f and replace it with what it's equal to. But notice that when I go to do this with function f, I'm going to replace, or I'm going to substitute in, or I'm going to use the argument of x minus 4. So anywhere in function f up here that I see an x, I actually have to replace that with an x minus 4 when I go to write that out. F of x is that square root of 1 minus x squared, but f of x minus 4 is going to be a little bit different. It's going to be 2 plus, so function f is this square root function of 1 minus, now again, instead of just x squared here, my argument is actually x minus 4 squared. So that's our direct substitution. If you wanted to simplify that, or if you wanted to square this thing out and simplify under that radical, you could. I'm going to leave it just like that. And let's grab our calculator and check this out. They asked us to verify that, in fact, this is the case. All right, so with your calculator, let's go to your y equals menu. And I'm going to go ahead and put in the original function that they gave us here in y1, just so we can see it along with the transformation. So it's the square root of 1 minus x squared And then in y2, let's put in the equation that we just came up with. And the equation that we just came up with was 2 plus the square root of 1 minus the quantity x minus 4 squared. All right, and let's graph this. I'm going to change the window here slightly because I don't need to see the window that the standard window here. Probably if we go from say negative 3 for our x's to maybe positive, moving over to the 5. So let's go to positive 6 here. I'm just trying to come up with a window that will show this nicely. And for our y's, let's go from negative 1. I'm only moving this up 2 units here, so probably if I go up to say 4, that will be decent. And we can graph that. And there we go. We've got ourselves a our calculator for some reason had a little bit of a blip there, it looks like on that red curve there. But anyways, this is our semicircle there. Your calculator does have a little bit of trouble sketching this accurately. It does actually come down to the x-axis for that blue curve there. But just based on how your calculator graphs, it did struggle there a little bit with us. But anyways, there's our original semicircle, and then we've translated 2 units to the 2 units up and 4 units to the right, it looks like. So that, in fact, looks like the right sketch. All right, that's the first way they said to do this. And in fact, I'll just grab a picture of that and put it in here. All right, the second way that they wanted us to solve this problem, they said direct substitution was A. Part B was using the grapher's built-in variable feature. So that's the function notation that they're talking about that allows me to do this transformation without having to actually do the algebra here to get this equation here. And what they mean by that is if my function g of x is equal to 2 plus f of x minus 4, and if I say that y1 is equal to f of x, we've already punched that in on our calculator. Now we've already typed in y2 was this g of x function from part A, so I'm going to have to use y3 for this. But in y3, what I can do, since I've defined y1 as f of x, I can actually write this as 2 plus, instead of f, it's going to be y1 of x minus 4. This is using the calculator's built-in function notation capability, or they called it the variable feature there. All right, so on our calculator then, let's see what happens when we punch that in. All right, so in y3 now, we're going to say 2 plus, and then we're going to say y1. And to get y1, if you go to your variables menu, go over to y variables, go to function, and you can grab y1 that way. And then it's x minus 4. Your calculator has this built-in understanding of what function notation is. That's a really cool feature that your calculator has. This one's going to come in black here, but I'm going to even change that one a little bit here, and I'm going to change it so it actually draws a little circle while it's sketching it, so I can actually see that show up. So pick the one that's got that little dash followed by a circle, and let's graph that. And I should see that it's tracing that graph right on top of that red curve there. So that in fact is the case, that the transformation of this function 2 units to up and 4 units to the right is in fact that red curve there. All right, and that's all they asked us to do there for example number 2. All right, let's take a look at dilations now. We'll tackle the vertical dilation first. And again, we're going to start with the same pre-image here that we've been working with the previous examples. That is our semicircle here, unit semicircle. And this time we want to dilate function f of x by a factor of 3 to get function g of x. Dilating, it means we're stretching it, or it could be shrinking it. In this case, we're going to stretch it by a factor of 3. If that factor is less than 1, then you're shrinking it. If it's more than 1, we're stretching it. All right, so let's set this up in much the same way here. Let's take a look at those same 3 points on the original function, the pre-image, and compare those to the corresponding points on the transformation on function g of x. So our starting points were at negative 1, 0, 0, 1, and then 1, 0. Those are the 3 points that we started with. And let's look at where do those points end up when we look at the graph of function g of x. So on function g of x, the point that was at negative 1, 0 stayed at that point. So that stayed at negative 1, 0. Now, the reason for that is because we're at an x-intercept there, and so when you do a vertical stretch at an x-intercept, nothing happens. So I guess the short story there is probably picking x-intercepts is not the best thing to do if you're looking for vertical dilations. But the one in the middle, that will help me out here because I can see that the point that was at 0, 1 is now up at 0, 3. And the last one, well, the last one was on the x-axis, and so I have the same problem there. It doesn't move for me, right? All right, so now the question is, well, how do these points here help me figure out how to go from one function to the other? And again, look at your x values and compare those. Look at your y values and compare those. I should see that my x values didn't change. It's my y values that change. So that's what I'm going to look at here. We shouldn't be surprised at that, by the way, when we say it's a vertical dilation. Vertical meaning it's a y direction, up and down. And the question is, how do I go from one set of values to the other? Well, it looks like, if I'm looking at these x values here, or sorry, these y values under function g, that those are 3 times as big. So if I take these y values I see here under function g and multiply them by 1/3 times 1/3, looks like I'll end up with the y values I see there for function f. So if I want to write this then, we'll start out writing it this way and then we'll modify that. But it looks like if I take each of the y values there for function g of x and multiply them by 1/3, so I'll write it as 1/3 g of x, that ends up giving us f of x. Each of the x values that or each of the y values that I see on function g, multiply them by 1/3, and I end up with f of x. Notice in this form, when I actually associate the dilation factor with the actual y value on the transformation, it turns out I'm actually dividing by that quantity. However, this is not how we normally write this. We usually put that dilation factor to the other side, and we'll write it as g of x is equal to 3 times f of x. And even though that might seem like the intuitive way to write it and the intuitive way to think about this, and the fact that we're stretching it vertically, so we're multiplying by a big number there of 3, really if I associate the dilation factor with the corresponding variable there, it turns out I was actually dividing by 3 to get that value. That's what that first line there shows us. Again, I'm going to come back to that idea here in just a second. All right, let's take a look at the horizontal dilation. So again, we'll start with the same pre-image there. We've got ourselves a semicircle centered at the origin with a radius of 1. We'll write down what our pre-image points are. So those were at negative 1, 0, 0, 1, and then 1, 0. And the question is, where do those points end up when we look at function g of x on the transformation? So the point that was at negative 1, 0 looks like it's been stretched all the way to the left there at negative 5, 0. And that's because we're dilating here by a factor of 5. That's why it ended up there. The point that was at 0, 1 stayed there, actually, it looks like. It didn't move at all. This is the same reason that we saw that the 2 endpoints on the vertical translation or dilation didn't move. If you're on the y-axis here and I dilate this thing horizontally, it doesn't move at all. Okay, in other words, probably something on the y-axis or the x-axis probably is not ideal for finding dilations, but here I have enough points that it will help me still come up with the result I'm looking for. I've got 3 points to consider. At the point 1, 0, it looks like that has been moved to 5, 0. All right, and again, the natural question we have for ourselves at this point then is, okay, how do I go from one set of data to the other set of data? Look at what's similar, what's different I should notice, first of all, that the y values haven't changed from the function f to the function g. And again, since we're talking about a horizontal dilation here, we shouldn't be surprised by that. So I'm comparing these x values then to these x values on each function and wondering how do I go from one set of data to the other. And again, if I look at how I go from what's on function g and how that gets me back to function f, these are all 5 times as big over here under function g. So if I multiply that by 1/5, but I'm multiplying the x values by 1/5, it looks like I end up with the values that I have on function f. So we should be able to write that then. It looks like that if I take g of x, that g of x is equal to f times 1/5 of x. And again, you might think about picking a value of x to plug in here just to make sure this makes sense here for us. For example, I'll pick the first one here of a -5. What do I have to do with that -5 in order to end up with the -1 that I see over there on function f of x? Yeah, again, if x here is a -5, and then I plug in the -5 over here next to the 1/5, -5 times 1/5, that would give me an f of a -1. Yeah, those are the same. That's what I'm trying to do. I'm trying to figure out how to go from one to the other. And again, the natural thing on this is to look at this probably and say, well, why are we dividing by 5 here on this one versus the previous one? It looks like we're multiplying. But again, if I associate the dilation factor with the corresponding variable, we're talking about a horizontal dilation, so it's affecting the x value. So that's why I've got the dilation factor of 1/5 times x. I'm actually dividing by that. And again, if I compare that with the previous one, the first way we wrote this, we'll see that we're actually taking this y value of g of x and we're multiplying it by 1/3. Multiplying by the reciprocal of our dilation factor really is what the operation is here. Turns out that's really what's happening in both cases. We're dividing by that quantity. It's not really a case that you're multiplying in one case and dividing in the other. It just happens to be that we rewrite the one that involves division as multiplication in one case. All right, let's take a look at an example. Again, we'll look at this same function here and analyze it in a similar way to with example number 1. With example number 2 was the equation for the preimage in this function that we're working with is again the same thing here. F of x is equal to the square root of 1 minus x squared. And it says to confirm on your grapher that g of x is equal to 3 times f of 1/5 x. And again, they want us to do it in 2 different ways. So for A, they say by direct substitution. So direct substitution means that we're going to take this function. This is the transformation of both dilations that we were just looking at. It's 3 times f of 1/5 x. So by direct substitution, all they mean is take this and actually substitute in what function f actually is, and then look at that graph, or graph that on your calculator. So we've got 3 times, and for function f, I'm going to replace function f with what it's equal to, but again, my argument here is a 1/5 x. So everywhere that I see an x here, I'm going to replace that with a 1/5 x as I write this out then. So it's 3 times the square root of 1 minus, instead of x squared, it's going to be a 1/5 x squared. Again, understanding what your function notation tells you and what that x actually means, or that argument actually means there. And again, you could simplify this if you want to actually square that out and rewrite this, but I'm going to leave it just in this form here. Let's verify that in fact this is this function that's been dilated in both directions here like we claim it has been. Grab your calculator. All right, so let's take our graph that we've got here, and I'm just going to turn off these two here. If you wanted to get rid of them, I guess you could, but I'm just going to turn off those two, and instead, in Y4, we're going to put in this transformation that we just that they just gave us here. I guess actually it's 3 times the square root of, and then it was 1 minus, and it was 1/5 of x, and we're squaring that. All right, 3 times square root of 1 minus 1/5 of x squared. Now let's go ahead and graph that. Again, oops, I need to change my window, don't I? Let's fix our window here. So let's go from -6 to 6 will be fine. And graph that. There we go. So that looks like that's been stretched not only horizontally, but it's been stretched vertically. So this, in fact, looks like the right sketch there. Notice that this one did a little better job of getting it to the x-axis, although it's not quite there. Again, just a little difficulty your calculator has in graphing this correctly. Just keep that in mind that most of the time it gives us the right sketch, but sometimes it's not quite right. I'll just paste a picture of that in there for us. And now let's graph this the other way. The second way they ask us to do that in this problem for part B is to do it by using your graphing calculator's built-in function notation feature is really what they're asking you to do. So again, what that means is if g of x is equal to 3 times f of 1/5 x, then on our calculator, we've already defined that y1 is equal to f of x. We've already used y2 and y3 and y4 now, so I'm going to put this in y5, I guess. In y5, then I can write this as 3 times, oops, not f, sorry, 3 times, I'm replacing f with y1. 3 times y1 of 1/5 x. Okay, that's how we're going to write that and see if we come up with the right sketch. So again, grab your calculator and let's try that out. All right, so under y5, we're going to put in 3 times y1. Again, that's your variables menu. Go over to y variables, grab your function y1, and it's 1/5, 1 divided by 5 times x. If you're not sure on order of operation, add a few more parentheses if you need to there, but that will handle it correctly. It will take 1 divided by 5 first and then multiply the result by x. And again, I'm going to change this just so we can see that sketch with that little circle there coming in. You can do the same thing. And if we graph this, we should see that on top of that pink curve there, we're seeing this little green curve getting sketched in there. And in fact, it is right on top. So that is, in fact, that transformation. All right, so what's the general equation look like then? Here is our general equation. If we take all of these transformations, put them all together, this is what your equation would look like. And definitely make note of this and definitely include all the parentheses that you see there so you get the right order of operations. In particular, it's knowing that first thing you're doing there inside those parentheses is subtracting that value of d from x and then multiplying the result by 1 over b. But y equals c plus a times f of 1 over b times x minus d. That right there is a transformation of function f with the following features. The value of a represents your vertical dilation factor. The value of b would be your horizontal dilation factor. The value c is representing your vertical translation. And the value of d is representing your horizontal translation. That right there is what we're trying to come up with. If I give you a sketch of one function and give you a sketch of its transformation, can you tell me the equation that represents all those transformations that took place there? There could be up to 2 dilations and 2 translations that took place. Here's what that equation would look like. Or vice versa. Maybe I give you the equation of the transformation and ask you to figure out what the original function must look like based on this equation here. All right, that is the first part of this section.